one is good. Okay, so everybody, I'm going to be talking today not about the Centre for Astrophysics, but about photoionization modelling that we've been doing. And this is sort of the culmination of work that we've been doing over the last about 6 years in order to produce much more accurate models for H2 regions and galaxies. And in particular, we're interested in modelling the star-forming regions at the epoch of reionization. And so just a quick summary of my talk today. I'm going to give an overview of the models and some interesting information about the photoionization model inputs, as well as briefly overview the different photoionization models. And then I'm going to talk about the effect of geometry. So geometry is critically important, as we now know, using IFU data of H2 regions. We can't ignore geometry. And so I'm going to then show you our work towards a fully self-consistent H2 region modeling, and then talk about the next generation photoionization models and some of their impacts that we're going to see in terms of our diagnostics and also our capability to model galaxies across cosmic time. So one of the motivations for this work is to really model star-forming regions at the epoch of reionization, and in particular we want to connect the emission lines and the ratios that we're observing with the Lyman continuum escape fraction. And so we need to be able to model the escape fraction and also the emission lines, so that we know with this type of figure here, where should we be lying in terms of the theoretical models, and what other factors contribute to those emission lines that we should be taking into account when we're using them to measure the escape fraction. So we all know that, well, in the metallicity field, we know that the oxygen 3 and the oxygen 2 lines are sensitive to metallicity. They're also obviously sensitive to the ionization parameter, which is why we're using it to estimate the Lyman continuum escape fraction. But what other things is it sensitive to? Is it sensitive to the pressure of the ISM? Is it sensitive to the geometry of those H2 regions at those redshifts? Quite likely it's sensitive to all these things, so we really actually need to be taking that into account. And so this is one of the main motivations for this work. Okay, so what we've been doing in the past is we've been taking stellar atmosphere models and stellar tracks, using them in stellar evolution synthesis models, and we provide them with an IMF, a stellar population age, a star formation history, and a metallicity, and then those provide the input ionizing radiation field into our photoionization models. We give it a dust model, and then we input an ionization parameter, an ISM pressure or density or temperature, a metallicity, and then a geometry, and then out comes a theoretical spectrum. It tends to be run in the community a bit like a black box. It's not a black box. You can actually change all these parameters, and you can actually understand the impact of all these parameters on the outcoming spectrum. And there's several models that are available right now. Two of the main photoionization models are Mappings and Cloudy. They produce almost identical outputs if you give it the same input parameters, and they give detailed photoionization and radiative transfer for up to 30 elements. And so the 30 element ability is very important for these models, because the elements act as coolants in a nebula, and so you actually have to have an accurate treatment of the elements in order to get an accurate temperature structure in the nebula. And then this is what allows you to derive an emission line distribution in a nebula that is accurate for the particular nebula that you're modeling. We also have different type of models, which are Monte Carlo ray tracing models, and two of these are Moccasin and CM, I don't know how to say that actually, Maclonize. And these are self-consistent Monte Carlo models. They're specifically for H2 regions. The problem is that they don't cover a large amount of elements, and they don't have the full set of physics that are in the photoionization models at the top. And for a long time we haven't had the computational capability to be able to combine these two techniques. And it's only been in the last few years that we've had this capability to be able to do this, even on a small scale, even for several H2 regions, for example. And so this is what we're aiming to do. And so one of the problems that we've had in the past with estimating parameters of galaxies or H2 regions is that we've been using these diagnostics. These ones are from Osterbrock. We've been using diagnostics such as the sulfur 2 lines, the oxygen 2 lines, nitrogen 2, oxygen 3 to measure density and temperature. And these all assume that you've got a constant density and a constant temperature throughout your whole nebula. And we're still using these diagnostics, but we know from our observations of H2 regions such as these observations of the Orion Nebula, that they're just not constant. There's hardly any H2 regions where the density and the temperatures are constant. So these figures show the electron temperature as a function of distance in the Orion Nebula, and also on the right-hand side, the electron density as a function of distance in the Orion Nebula. And you can see that there's this interesting distribution, and it really just depends on which H2 region you're looking at, where you're looking at in the nebula. And Orion's quite turbulent. So Orion has very complex structures, and in both temperature as well as density. And so this is something that we expected, but we also need to know whether this applies to many H2 regions or not. Now we can now model complex temperature and density distributions, and so these are models of the temperature distribution on the top panel and the density distribution on the bottom panel as a function of thickness through a nebula, and with different metallicities. And so it depends quite a lot on metallicity, and that's just because your metals act as coolants, and so it changes the electron temperature and the density structure of the nebula. Now, so new photoionization grids, they should allow temperature and density to vary through a nebula, and indeed that's what we've been doing. But the question is this really enough? Is it really enough to model the H2 regions that we observe? And so what we did was we wanted to go and measure H2 region temperature and density maps. And very surprisingly, this hadn't actually been done for many H2 regions. And so we went and looked at some simple ones. So these are single star H2 regions in the LMC and the SMC, because we wanted to see what the temperature and the density maps look like. And in Australia, we had a great telescope for this. This is work done by my PhD student, Yufei Jin, who's now at CFA. And we used the wide field spectrograph on the Mount Stromlo 2.3 metre telescope, and it has really a perfect field of view for H2 regions. So it's 25 by 38 arc seconds, and so H2 regions within the LMC and the SMC fit really neatly within the field of view, and then that gives us, you know, a large number of spaxels across the whole H2 regions. And I should emphasise that observing in Australia is extreme astronomy. And so we go out to the telescope and we have these red-backed spiders. They're poisonous. We have red-bellied black snakes, and they are also very poisonous. We have brown snakes. Now, my son told me when he saw this light, he said, "Oh, I stepped on one of those one time." And he hadn't told me at the time because he thought I'd be worried. Very dangerous. We also have these, you might not realise, but our koalas, if they're, some types of them are very territorial, and they actually are quite aggressive, and they can drop out of trees onto you and attack you, especially when they've got young around. They're called drop bears. And we also have bushfires. You also have bushfires, and we have very dangerous kangaroos. So it's a wonder that we were even able to get these H2 regions at all with all these dangerous creatures and things happening at the telescopes. So here's what they look like. So the H2 regions up here, that we have the temperature structure shown for each of the different H2 regions, measured using different lines. So we've got nitrogen 2, oxygen 2 and oxygen 3 temperature structures. And it really varies from H2 region to H2 region. You wouldn't be able to say that they're homogeneous at all. And when we compare them with those theoretical models that I showed you earlier, the models are in black, and the blue, red and green distributions here are the observed temperatures of those H2 regions. And we did tailored models for every single H2 region. The models don't do a good job at all. And so what's wrong? Why is it that we can't model the temperature distribution with our traditional photoionization models? And the answer is geometry. So we've been assuming that the models are plane parallel or spherical when they're just not. So if you look at the H2 regions, you know, they can either be bipolar, they can be blister-like, they can contain many concentric shells and other structures. They are not remotely spherical, and this is the main problem. And so over the last few years, we've been developing Monte Carlo, detailed Monte Carlo photoionization models towards an accurate treatment of the radiative transfer, cooling and heating across all the 30 elements. And so this is one of our models, and we're just doing 360-degree zoom around of this model. And on the right-hand side, there are cuts in different planes, and you can see the emission lines in those. So the top shows H beta, the middle shows oxygen 3, and the bottom shows N2. You can see you have quite different distributions for each of those emission lines in the nebula. And so if we look at and observed as if we were observing these, so the line of sight images from the theoretical spectra, they're up in the top. So these are theoretical IFU data now. And so we've got nitrogen 2 in pale blue, oxygen 3 in red, and H beta in sort of a dark bluish turns green. And you can see it's much more similar to what we would see in regular H2 regions. Now, these are still simple models. These have a single central ionizing star. They have a solar metallicity, and they're radiation bounded. So this is the first step. This is sort of a test case for these models. And what we can do with, one thing we can do with the models is we can look at the influence of orientation on the line of sight emission lines. So, for example, if we drew a slit, or we're looking across these H2 regions along this particular axis here, then you can look at the intensity of the emission lines across the H2 region. And so you can see how an H2 region depends on orientation and which part of the H2 region you're actually looking at. And so this is important to take into account. And then the complex geometry changes the emission line distributions, and it actually drives fluctuations. So on the right-hand side of these panels is the original spherical model for those H2 regions, and on the left is our fractal geometry. So we're doing fractal geometry. And one thing that is really important to point out is that specific emission lines are produced in the edge of the nebula, and so it actually increases the perimeter, or the regions at which some emission lines are actually produced. And the bottom two panels are metallicity sensitive lines, so R23, and we've got an ionization parameter sensitive line ratio, oxygen 3 and oxygen 2. And again, the distributions are wildly different from the spherical case. And this is another nebula that we modelled, and this one we're specifically looking at a boundary line. So the bottom panel here, the oxygen 1 line and the sulfur 2 lines in particular are produced in the edge of the nebula in a sort of a partially ionized zone. And so in these type of models in a fractal geometry, you actually see that these are produced in a very extended zone all around the edge of the nebula. And what that means is that you get more of these lines if you have a nebula that's a fractal geometry compared with a spherical geometry. So in real life, we expect to see more of these lines than we can measure if we were using a spherical geometry model. This has important implications on our ability to measure the emission lines and use them as diagnostics in galaxies and H2 regions. All of our previous diagnostics are based on the assumption that we have a H2 region that is plane parallel or spherical. And so this shows you the difference between the 3D and the 1D. So the top figure, we're taking the 3D model and we're dividing it by 1D. And so we have a variety of emission lines here. The Balmer lines don't change. That's to be expected. They're produced throughout the nebula. But we see that the sulfur 2 and the oxygen 1 lines are much more strongly produced in the 3D model than in the 1D model. And again, it's impacting the sulfur 2 to H alpha and the oxygen 1 to H alpha ratio. And you can see here why. It's because the oxygen 1, which is shown in green, and the sulfur 2 in yellow are produced at the very edge of the nebula. And so this is important for all the lines in the UV, optical and infrared because we have specific boundary species in those parts of the spectrum. And so if we look at an integrated emission line spectrum now, so we're now integrating the model, we can compare the difference between the equivalent spherical nebula and the fractal nebula. And the difference is shown in particular on the right-hand side figure there, where we have the emission line flux using the old version of mapping. So that's the spherical, so the 1D spherical model on the y-axis, and then on the x-axis is our new fractal nebula fluxes. And if they agreed, they'd fall along the 1-to-1 dashed line. But what's happening is that we've got lines like oxygen 35007 and sulfur 2, even nitrogen 2, which are produced produced in different amounts in the fractal nebula compared to the mappings models. And so this is then going to impact all sorts of diagnostics, from the optical diagnostic diagrams to metallicity diagnostics, ionization parameter diagnostics, and so on. So we're now running a big grid of models in order to recalibrate those diagnostics using the fractal geometries. This shows you the impact of the spread of emission lines on the optical diagnostic diagrams. So for those of you familiar with optical diagnostic diagrams, this is a good way of separating star-forming galaxies from AGN, and also we see an H2 region abundance sequence. So the grey points here, these are actually our models, the grey points. So we have low metallicity H2 regions lie here, and high metallicity H2 regions lie up here. Previously, with spherical models, we weren't able to reproduce the full range of data with these types of models. They really were lying in a very small part of the diagram, and now with the complex geometry, we're actually able to reproduce much better the full distribution that we would see of H2 regions on these optical diagnostic diagrams. Also, we can have a look at the UV emission line flux. And so it does change the UV emission line flux, and in fact it has a significant impact on the UV emission line. So this is relevant to JWST data. And so in particular for the carbon 31908 line, it's a 22% difference. The carbon 4 at 1548 is 26% difference. Oxygen 3 at 1660, 23%. The nitrogen 4 at 1483, 27%, and nitrogen 4 at 1486, 27%. So there's actually about a third change in flux for these lines. They get larger with our fractal geometry than we had with the spherical geometry. And so to wrap up, we were like this, spherical, we're assuming spherical. We're not there yet. We're only in the middle here we've got maybe a little cow with a little head, but we don't have the full features in terms of how well we can model our H2 regions. And so we're getting there, but I just want to spend the last bit of my talk talking about what we have to do next. So now we're running a large grid of complex geometry nebula. And with this large grid, we want to then recalibrate the diagnostics that we had in the past. That's starburst, AGN classification, metallicity, ionization parameter, pressure. But we need to set the physical geometries in the nebula. And how are we going to set the physical geometries? Well, we need to use magnetohydrodynamic codes of star forming, of the gas around the star forming regions, to really identify what those geometries would be expected to be like, so that we can have a more realistic geometry for our H2 regions. That's the next step. Then we want to combine the mappings 3 code with illustrious TNG cosmological simulations. So we're now at the CFA, we're working with Lars Hörnqvist and his group with the illustrious TNG simulations. And then with our new self-consistent complex geometry diagnostics, we plan on measuring the co-moving star formation and metallicity history of galaxies using consistent diagnostics across the full wavelength range from the UV through to the far infrared. And then the other goal of this project that I mentioned earlier is to get more accurate estimates of the line ratios versus escape fraction. So we'll be able to put models on the figure of oxygen 3 divided by oxygen 2 versus escape fraction, and any other lines that we're using right now. We're also looking into the use of equivalent widths and what also impacts the equivalent widths aside from escape fraction, so that we can calibrate these with our models and the model parameters as well. And we want to be removing any of the contaminants. So if metallicity is a contaminant, if pressure, if we have other contaminants in their geometry changes the ratios, we'll be able to take that into account, or at the very least see how much it impacts your errors when you're actually making the measurements of the escape fractions. Thank you. switch microphones.
Thank you. Time for questions.
So it's interesting in your new model, the way the BPT diagram, you now get this greater spread. Earlier you were showing IFS data of individual H2 regions where some were more spherical, some were more non-spherical. Does that change? Do you see that in the real data, that the more spherical ones are along that upper line where your spherical model was, whereas the more aspherical ones, more non-spherical ones are more offset? Like,
depends on the orientation as well. So which orientation you're looking at them from, and then you need to we integrate along the line of sight to be able to mimic an IFU data cube that we would get. So it does depend on orientation, but certainly with the different geometries, each of those data points, the model data points on there in grey, were a single spaxel. A single modeled spaxel. Okay. So they're not individual H2 regions, they're separate spaxels. I'll bring that back up again if I can.
Because what I'm wondering is whether it's so hard to go get integral field spectra on 1,000 H2 regions with these different geometries. And I'm wondering if there's a way that you can infer from the observed distribution, like a spherical probability distribution or something of actual H2 regions.
Yeah, it's a good point. Once we've done the big grid with multiple geometries, then we can certainly have a look at that and see if there's any correlations with different geometries or different orientation angles that we might expect them to be in different parts of the diagram. Completely agree. It was hard enough just to get those 4 H2 ridges. We've now got like a dozen. Would be wonderful to have 1,000, but that's not happening for a while.
Hi. Are you worried that the presence of stellar wind bubble would actually completely change the structure of the H2 regions?
Yes,
are you
considering?
Considering?
Yeah, so stellar wind bubbles absolutely will change the structure, and so that's one reason why we want to use the magneto-hydrodynamic models. They have the stellar wind bubbles in them, and we want to use that as the input for our geometry for the next phase of the models. Yeah, definitely.
So we can have one quick last question, and our next speaker, please setting up.
Thank you. Interesting development. I was wondering what are you prescribing for the fractal dimension and the amplitude of the fluctuations, because I think it's so you're working in real space. Wouldn't it be better to use, given that we know the fluctuations are produced by turbulence, to work in the power in free space, so you can prescribe the power spectrum rather?
Yeah. So at the moment, these are still fairly simple models, but we're using a log normal Gaussian type distribution for the fractal geometries.
Thank you, Lisa.